for Chern-Simons theory on the two-sphere is two-dimensional. And here we're taking the gauge group G to be SUN. And at the positive points, there's a fundamental Wilson line. That is a Wilson line in the fundamental or the vector representation of SUN. And the negative guys, there's an anti-fundamental. So the first challenge this presents is that we don't really know, given a Lagrangian, how do we compute the Hilbert space? You probably know some examples of this. You've probably seen this for a scalar field theory. But Chern-Simons theory is a bit funny because it has a first-order action as opposed to the more familiar second-order actions. So you can't always use your intuition from studying scalar field theories and apply them to Chern-Simons theory. But there is a general ansatz. So we're going to revisit this topic later, I hope. So I want to present a sketch of general ansatz for computing the Hilbert space of any theory. And when applied to Chern-Simons theory in the two-sphere, it will be very, very simple to apply. Yeah, the ansatz is the following. For any field theory, not necessarily topological. First, study on a manifold M times this manifold we can think of as space times a small interval. We study the space of solutions to the equations of motion. So call this X, or call this, say, equations of motion of M. So there's some technicalities. If we're dealing with a non-topological theory, we have to think, am I working in Lorentzian signature or am I working in Euclidean signature? For topological theories, it's the same thing. For non-topological theories, this procedure works for both, but Lorentzian signature is slightly better behaved. In Euclidean signature, what you need to do is you solve the equations of motion in series in a coordinate here. Those series may not converge. That's okay. And then the claim is, so because we are studying a PDE, which is of a variational origin, this space has a natural closed two form. Call it omega, so that there are coordinates pi, qi, where omega is equal to sum dqi wedge dpi. People might be familiar with the Peere's bracket, and this is just the same thing. So omega inverse is what's called the Peere's bracket.
Sorry.
Mm-hmm.
What do you mean by variational origin?
Well, it wasn't just any PDE I started with. I started with a PDE which came from varying some action functional.
Yes. So what is origin? The origin is origin what?
The PDE. So,
I think it's an English problem.
Oh, yes.
The PDE came from varying the action. That's the origin. Yeah.
Oh, okay.
Yes, sorry, yes, absolutely.
Terminology, sorry.
Yes, exactly, yes. So if you take some random PDE, you won't have this structure. But the fact that the PDE was given to you as an Euler-Lagrange equation gives you this extra structure on the solution set. And then the Hilbert space is equal to an appropriate space of functions of half the variables. Say qi. So in general, this part, there's a bit of a, so the first step is totally algorithmic, and this second step of like choosing which half of the variables should I consider functions of, and what kind of functions, what kind of growth rates should they have. There's a bit of an art to this step. But if you do it right, it shouldn't really depend too strongly on the choices you've made here. So this should be fairly familiar. So for example, quantum mechanics. I have this Lagrangian. Phi is a map from, say, OR to OR. Well, in this case, what I'm calling M is a point. And then the solutions to the equations of motion on what I've called, I've associated this, I've called my manifold of solutions to equations of motion, I've associated to space instead of space-time. Since here space is trivial, I'll just write EOM. This is the set of phi functions on a small interval whose second derivative vanishes. Now we know how to parameterize these. Every such is determined by its value at the origin and its first derivative at the origin. So phi, any such phi, is phi equals phi of 0 plus p phi prime 0. So the space is two-dimensional with coordinates p, which is the momentum, and q, which is the position. And the natural symplectic form is dp dq. And in this case, then the Hilbert space well, of course, we should take functions of half the variables, and this gives us the correct answer. This is the correct answer. So you notice that it was important that we took functions of half the variables, otherwise I would not have got the correct answer for what the Hilbert space is for quantum mechanics. A state is not a function of position and momentum, it's only a function of one of them. Any questions?
In the case of, for example, the scalar field, the bracket is constructed by studying the Green's functions of that quadratic form.
That is one of the ways to construct the bracket, but you.
Oh, okay. So it won't be a problem that our form is not quadratic in your assignments.
Why do you mean the form is not quadratic?
Yeah, because didn't we construct it by studying?
You mean because we don't have a free theory, or?
Because what we were studying were precisely this Green functions that were retarded and advanced for that free theory, right? And here, what will be the analog of that free theory operator?
Oh,
who's
I mean, I think you could be making this complaint in general that. Oh, let's see. I mean, in general, it is not true that this expression can be written down just in terms of a free theory. So it is possible. I don't want to get into the details of how you construct this. It is possible to construct it without any reference to Green's functions. So it can be treated entirely by thinking just. There's some very geometric way to do it, which I don't want to get into. If you want to study it using Green's functions, the abstract way to do is to say, well, I want to have a Poisson bracket in my algebra of operators, and I just compute it using Feynman diagrams. And one of the terms will be I exchange, there's a single line exchanging them. There could be other terms. And I'm taking a semi-classical limit, so I only extract the terms that appear at one loop. But that's a general procedure that always works.
Do you have any recommended places to read about this?
There's some notes on symplectic manifolds by Graham Siegel from the 90s. Like, they're handwritten and they used to be on the internet. I thought they were pretty good.
Okay.
Can you get the same information from Owen's thesis? We did this.
Oh, yes.
We did this. It's from Owen's thesis.
For Chern-Simons theory, he studies this.
No, for any field. This always holds.
This always holds, yes.
But it's just, I don't want to get into the detail why that's true, but it's going to in that framework. You can get the structure always.
Yes, that's true. Yes, absolutely. For free theories.
Yeah.
Yeah, and Owen's thesis does give you the construction for any free theory. That's right. Maybe as we'll see later, I mean, for Chern-Simons theory, the natural coordinates on this space are given by Wilson lines. So when you do the Peierls bracket, you're going to take a Wilson line here and a Wilson line here and try to move them past each other. And you're going to end up computing their things like the linking number. So it's for Chern-Simons theory, it's not that crazy. Okay. But I didn't want to get into this too much because, like, the study of the symplectic form, oops, sorry, wrong one, is quite subtle. Or for the examples we want to consider today, all of the examples we're going to study, the space of solutions to the equations of motion is a point. So that's what's nice about topological theories. Once your space of solutions to the equations of motion is a point, you know what to do with the Hilbert space. It's like C. So let's do some examples. For Chern-Simons theory on S2 with no Wilson line insertions, the equations of motion say that the curvature of my gauge field vanishes. So in general, if we have a manifold M, and a gauge field, on M with f of a is equal to 0. So I want to explain kind of a general result about describing the set of such things. If all loops in M tau r can be contracted to a point, so this is called being simply connected. Then FA is equal to 0 implies A is gauge trivial. Now, so S2 has this property. So this fact here, if M is simply connected, then all gauge fields with vanishing curvature are gauge trivial. This is some not super hard fact of differential topology. So the intuition is the only way you can distinguish your gauge field from the trivial one is by measuring what it does along a closed loop. Now, since the field strand vanishes, that measurement doesn't change if I change my closed loop. And if M is simply connected, I can just shrink it. Then that measurement becomes the identity. So it's kind of physically plausible that this is true, and it's an easy result in differential topology. Okay, so we find that the space of solutions to the equations of motion on the two-sphere equations of motion are a point, and therefore the Hilbert space is C. Okay, so this is consistent with something we discussed before. A topological field theory is, in particular, a conformal field theory. Conformal field theories have a state operator correspondence relating the Hilbert space and the sphere to operators. And we argue that Chern-Simons theory had no local operators because of this. This equation means that on a ball, everything is gauge trivial. It's consistent with that argument. So you note that if I was to try to do this for some other surface, like a torus has lots of interesting loops, and I would get a much more interesting answer.
So the UMs are taken up to gauge symmetry.
Yes. I want to say a little. So in the tutorial, I asked you guys to study the equations of motion for Chern-Simons theory for the group U1 with Wilson line insertions. And we saw that there was some quantization property. So I want to try to explain what that says about the Hilbert space for Chern-Simons theory for U1 with the Wilson line insertions. So G equals U1, then Chern-Simons action, which looks like the integral of K over 4 pi I. I'm terrible at getting all these factors right, so I do apologize for that. And we want to add, this is going to be on S2 times OR. We want to add Wilson lines at Pi in S2 of charge Li, so that we get integral S2 times OR K over 4 pi I ADA plus integral over Pi times OR LIA. This is my Lagrangian.
So why did you say that the action was not quadratic? Now that I think of it.
I didn't say the action was not quadratic.
Oh, I thought that. And
I think you once asked a question about the 5D analog of Chern-Simons theory.
Yes.
And that is not quadratic.
Oh, okay.
That is not a well-defined theory because it's not quadratic.
Okay.
Okay, so we saw that if we solve the equations of motion, tell us that f of A is equal to sum Li over K 2 pi Lj I delta function Pi. So we claim that we can solve this if and only if sum Lj over K is an integer. And then there is one solution. So the Hilbert space is C. So otherwise, the Hilbert space is 0. So I know I asked you to study this in the exercise, but I thought I'll just write down the solution, and you can see why it only works if we have this integrality constraint, just because it's kind of fun. So what we do is we write S2 as complex numbers union infinity. And then A, we said A equals sum Li over K 1 over Z minus Pi dz away from infinity. So you think about, I don't want to spend too much time on this, but if you think about Cauchy's theorem, it tells us that d of this expression is a delta function. So d of 1 over z dz is 2 pi I times the delta function at z equals 0. This is essentially Cauchy's formula. So why is that? Cauchy's formula, I have a function. If I integrate something over the boundary of a disk, then by Stokes' formula, that's the boundary of an integral of d of this thing over the middle. Since the integral over the boundary is 2 pi I times the value at the origin, implies that d of this must be the delta function at the origin. Okay, so we can ask, how is it possible to extend this to infinity? If we look at this expression, so near infinity, this has a pole, and that's bad. A looks like sum Li over k dz mod z, which has a first order pole at infinity. At infinity. So, can we remove this by a gauge transformation? And the answer is yes. So we let f of z be the product of z minus pi the Li over k. And then f inverse df is equal to a, as is clear. So if f is single valued near infinity, then we can remove the singularity at infinity. So this happens if, so when z is very large, these p's don't really matter. So the single valuedness is only about the sum of these Li's over k. Okay, any questions?
Sorry, maybe a silly question. Why is there a pole at infinity instead of at 0? Why is a pole at?
So here?
Yeah.
Oh, because if I say u equals 1 over z, then dz over z is minus du over u, because du is minus u to the minus 2. So, okay, so we've done, so we understand the Hilbert space of U1 Chern-Simons theory with arbitrary Wilson line insertions on the two spheres. So that's a good start. One of you was mentioning that Chern-Simons theory for the group U1, the Wilson line of charge k is actually the same as the Wilson line of charge 0. We're kind of seeing this. So for U1 Chern-Simons theory at level k, Wilson line of charge k is in fact equal to the Wilson line of charge 0. So we're seeing why the Wilson line of charge k as a state at the end of the Wilson line of charge k, the state we've just constructed because it arises from this magnetic monopole, is an interface between the charge 0 and charge k lines. So the picture is, the Wilson line of charge 0 is really nothing because I put 0 next to the integral of A. So I can relate the Wilson line of charge 0, which is nothing, with the Wilson line of charge k by this, and the thing that lives here is the monopole state. So this is getting a little more advanced into TFT axiomatics, like when are two defects the same? But this interface, it turns out, gives you an equivalence between this guy and this guy. Okay. Any questions? So let's turn to what we really wanted to do. So we understand U1 with Wilson line insertions. We understand any group with no Wilson line insertions. So what happens if we take some arbitrary group with Wilson line insertions on the T-sphere? What does the Hilbert space look like? So there's a missing ingredient, which is what does a non-abelian Wilson line contribute to the Hilbert space? So for an abelian Wilson line is just a term in the Lagrangian, because an abelian Wilson line is an exponential of something. Now, a non-abelian Wilson line is not an exponential. It's a path-ordered exponential. So we have to be much more careful when we try to think about what a non-abelian Wilson line contributes to the Hilbert space. But to understand what's going on, I want to explain why Wilson lines are coupled quantum mechanical systems. So consider a gauge theory with a Wilson line, say fundamental for SUN. And let's treat the gauge field as a background a classical field. So that means I don't want to think of the gauge field as for now, I don't want to think of it as a fluctuating object in the path integral. It's just some fixed thing, like Maxwell would have talked about. And so the Wilson line is defined by the parallel transport. Suppose I take an initial, I'm going to call it a state. We have the equation d by dt of psi of t times dt is equal to gamma star of A. I say it was like this. Plus gamma star of A psi of t is equal to 0. Where gamma or n is the path. And we notice, because we're doing with the gauge group SUN, gamma star of A is equal to dt times m of t, where m of t is an n by n Hermitian matrix. Okay, so write it out more explicitly, that d by dt psi of t plus m of t psi of t equals 0. So I hope this equation is familiar to everybody. The Schrodinger equation. With a time-dependent Hamiltonian, which couples, which is
So this is a Schrodinger equation in measuring time.
Did I get the factors of I wrong? Well, no, it's a
Hermitian. I think with your conventions, it's probably anti-Hermitian. So the I
You mean
is like
M is
multiplied by N.
okay. I see, because it's
Because you're writing the Lie algebra as the group.
yes. Okay. Yeah, I was worried I missed a factor of I, but I. So. Anti-Hermitian. So this is a good question. So if I take some other gauge group and some other representation, does it look like the Schrodinger equation or does it look like the heat equation, which is the imaginary time version? It seems silly to call the heat equation the imaginary time Schrodinger equation when like you see it every time we turn on a radiator. But that depends on the structure of the representation, if it's a complex or real representation. And this is a complex representation. Okay, so what does this tell us? A Wilson line is just the same thing as a quantum particle traveling along gamma with Hamiltonian gamma star A. Now, of course, from this description, it's obvious what the Hilbert space of a Wilson line is. Then, obviously, yeah, say Cn, or whatever representation we're using. So let's now study, say, S2 with, as before, say 2 fundamental Wilson lines. I'm going to write this as V equals Cn, and 2 anti-fundamental. V star, which is the same as a complex conjugate, which is Cn bar. And I'm going to consider this in a regime where the Chern-Simons Lagrangian is weakly coupled, and over here I'm going to have times of Wilson lines. Now, this is a little different from the U1 case. Right? The U1 case, this H bar was a number. Yeah?
Sorry, I cannot read what it says behind CS.
1 over H bar. Okay, is this blackboard visible at all, or is this?
Yeah, I think it probably is my eyes. Sorry.
Need glasses? Yeah, yes. Yeah, handwriting should be bigger. So the point is, the equations in the U1 case, the equations of motion for the gauge field had a contribution of order 1 from the Wilson line. Here, because of this prefactor, the equations of motion will have a contribution of order H bar from the Wilson line. So will be like f of A is equal to 0 plus order of H bar. So plus quantum corrections. So this is the dominant term. In other words, so there's some the coupling between these guys can be treated as weak. So the Hilbert space at first pass, the gauge fields give just C, and the Wilson lines give, well, there's 2 fundamental and 2 anti-fundamental. However, we've forgotten something, which is that the trivial gauge field has the constant gauge transformations are symmetries of the trivial gauge field. So we have to project onto the gauge invariant states for the Wilson line contributions. So A equals 0 has constant gauge symmetries SUN So we need to project onto gauge invariant states. And these are okay. So let's ask the question, like, what are the gauge invariant states? I have here, this is a 4-index tensor. Let's be like this is star instead of bar. This is some tensor I'll call x. X has 2 lower indices and 2 upper indices. What are the SUN invariant quantities that I can construct from a 4-index tensor? So SUN invariant means that they're scalars. And it's pretty obvious that if I want to construct a scalar from this tensor, I must contract the indices in some way. There are 2 of them. Which is what we wanted. They are x, I, j, j, and x, I, j, j, I. Okay, any questions?
In SU2, we have this metric, this epsilon metric, and using it we can construct other things.
Yeah, you think you can, but actually it turns out they're not independent. Just by thinking about for SU2, I would think about it in terms of representation theory. This is like a 16-dimensional space. And this piece here, 4-dimensional, looks like the adjoint plus the trivial. This piece looks like the adjoint plus the trivial. And then you know there's a 1 invariant tensor in the adjoint tensor of the adjoint, and 1 in the trivial tensor of the trivial, and nothing in the adjoint tensor of the trivial. So there's still 2. Okay, so we can picture these. So modulo h bar. So let's see. Let's think of a good way to picture these guys. Let's view these guys, these tensors, as linear operators on V tensor V. And then the two in some basis, the 2 tensors are the invariant ones need a new blackboard. So there's 2 obvious things I can do. The identity matrix and switch the 2 factors. So the identity, V tensor V to V tensor V, it just sends a tensor product to be the same thing. And the permutation, I'll call it rho V tensor V, V tensor V, and it switches the 2 factors. Okay, now, so modulo h bar That is, so ignoring any quantum corrections, we draw our link diagrams. Here I have two incoming things. V, 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 V. So the one where they don't cross each other, that's the identity. And the one where they do cross, this is the permutation, which I'm calling rho. So this one might have quantum corrections because of gluon exchange when the lines get close to each other, plus OH bar. But this one is also the same thing. So we're almost at the state of seeing that because the Hilbert space is two-dimensional, there must be some kind of Skine relation between them. Like, we can say that already. And we can even see what it looks like modulo h bar. There's going to be one-loop corrections. Because the Hilbert space is two-dimensional, we must have a relation like F plus H bar plus F minus H bar plus F0 H bar is equal to 0. We can also see what this relation is to leading order. Modulo H bar, F plus is equal to 1, F minus is equal to minus 1, and F0 is equal to 0. But then there's going to be quantum corrections to this, and we can compute the first quantum correction next time. Yeah.
You mean Hilbert space is C2, we are in SU2 group?
So no, this is true for SUN. Hilbert space on S2 with two fundamental and two anti-fundamental Wilson lines. For SUN, yeah.
I'm sorry, so this C2, which are these two bases of C2?
Right, it's not, this C2 is very different from the SU2. It's not any representation of SU2, because we've projected, it was this analysis here where we project onto the gauge invariant states.
Yes, yes.
And there's two gauge invariant states depending on the two way of contracting the indices. So the C2 has basis the two ways of contracting these indices. So a basis for C2 is given by, say, the lines are parallel, it's the identity matrix, or they cross. So next time I want to explain why, if you compare these guys at order h bar, they're no longer the same, because when I bring these guys together, there's a kind of UV singularity related to the exchange of a single gluon, which means that this minus this is h bar times this with some coefficient. And we can calculate the coefficient and try to match it with the Jones polynomial. I tried to calculate it this morning, but a factor of 2 was wrong. Okay, so I'll stop there.